Let's talk about the strange way tiny things behave in our world. Things get really interesting when we look at stuff smaller than what we can see with our eyes, like electrons or photons of light. Back in the labs of the 1960s, we had these big electron guns, like the ones in old television sets, shooting beams of electrons at screens that glowed when they hit. It was fun to watch, but it also showed us something wild that doesn't make sense in the everyday world. Imagine trying to explain how light or electrons act using only ideas from big objects like bullets or water waves. It just doesn't work. That's the heart of it all. We have to think differently. First, think about shooting bullets at a wall with two small holes in it. Suppose the wall is armor plate, so bullets don't go through unless they hit a hole exactly. Behind it, there's a backstop to catch them. If both holes are open, bullets go through one or the other and pile up in two clumps on the backstop right behind each hole. If you close one hole, you get half as many in the clump behind the open one. Simple. The probabilities just add up. Now try the same with water waves. Send ripples across a tank toward a barrier with two openings. On the other side, the waves spread out and interfere. Where crests meet crests, you get bigger waves. Where crest meets trough, they cancel. You end up with a pattern of high and low spots, not two simple piles. Light does the same thing. In the old days, we'd shine a bright lamp through slits and see bright and dark bands on a screen. Light acts like waves. But here's the surprise. Electrons, those tiny bits that make electricity flow, do both. Fire a beam of electrons at two slits, like in those 1960s experiments with phosphorus screens that lit up where electrons landed. With both slits open, you don't get two clumps. You get a whole pattern of bright and dark stripes, just like waves interfering. Turn down the beams so weak that electrons come one at a time. You hear little clicks on a detector or see tiny flashes on the screen. Each electron hits one spot like a particle. But wait a while, let thousands arrive slowly, and the spots build up into that same interference pattern. Each electron lands like a bullet, but the places they choose to land follow wave rules. If electrons were just particles, they'd go through one slit or the other, and we'd see two piles. But they don't. It's as if each single electron goes through both slits at once, interferes with itself, and decides where to land based on that. Of course, you might say, let's find out which slit it really goes through. Put a light behind the slits to shine on the electrons as they pass. In the lab, we'd use a strong lamp to scatter light off them. If light bounces from near slit 1, it went through 1, from slit 2 through 2. But when we do that, back in those careful setups from the 60s, the interference pattern vanishes. We get two clumps again, like bullets. The act of watching which way it goes forces it to choose one path. Without watching, it takes both. That's the puzzle. Nature doesn't let us see it acting as both wave and particle at the same time. Try to pin down the path, and the wave interference disappears. Now, how do we make sense of this? We use something called probability amplitudes. These are like little arrows. Each possible way something can happen gets its own arrow. The length of the arrow relates to how likely that way is. Actually, the probability is the length squared. The direction of the arrow comes from a kind of clock, a stopwatch that turns as things happen over time or distance. Imagine each electron has a tiny stopwatch starting when it leaves the gun. The hand spins fast, really fast, depending on the energy. For different paths to the same spot on the screen, the stopwatch hands end up pointing different ways because the paths are different length. To find the chance of arriving there, add all the arrows head to tail. The final arrow's length squared gives the probability. If paths are almost the same length, arrows point nearly the same way, add up long, high probability. If one path is half a wavelength longer, like in waves, the arrows point opposite. Cancel out dark spot. Low probability. That's why we get the striped pattern. All those possible paths interfere through their arrows. Think about why a thin sheet of glass partly reflects light. You look in a window at night and see your face faintly while mostly seeing through to outside. About 4% reflects from ordinary glass. Why not 0 or all, or 8% from two surfaces? Light photons come in, some reflect off the front surface, some go in, bounce off the back, come out. But it's more than that. In reality, reflection can happen anywhere in the material. But we can think of main contributions from front and back. Each photon has arrows for reflecting from front or from back, after going in and out. The key is the arrows have phases, like the stopwatch turning extra for the longer path through the glass. When opposite, they cancel almost no reflection. When same, they add more reflection, up to 16% or so. In the lab with precise thicknesses or monochromatic light from early lasers in the 60s and 70s, we'd see it cycle. Thick glass reflects a lot, then less, then none, then more, as thickness changes by fractions of wavelength. But shoot one photon at a time. Dim light clicks on a photomultiplier detector. Each click is whole reflection or transmission, no half photons. Yet over time, the probabilities follow the arrow additions. The arrows explain partial reflection perfectly. This arrow idea is powerful. For any event, some arrows for all ways it can happen. Square the result for probability. In big things, most arrows cancel, except near the classical path, like light rays in optics. That's why everyday world looks classic. But for tiny things, many paths contribute. Arrows interfere wildly. Now this leads to what we call superposition. Before measuring, the system has amplitudes for different outcomes. It's not that the electron is definitely in one place or another. It's amplitudes for all possibilities, adding up. For example, polarized light with filters, like those Polaroid sunglasses popular in the 50s and 60s. Light can vibrate up, down, or side. Pass through a vertical polarizer, only vertical gets through. Then another vertical, all through. But tilt the second to 45 degrees, half gets through. Add a third at horizontal, none. It's amplitudes, adding at angles. The light after first filter has amplitude for vertical. To go through tilted filter, we break into components. Arrows at angles add vectorially. Superposition means amplitudes for different polarizations coexist until final measurement. We're getting close to bigger questions. People wondered in the old days back to the 30s. But we were still debating in the 60s and 70s if this superposition applies to larger things. Suppose something small like an atom decaying radioactively triggers a counter which releases poison in a box with a cat. If the atom has 50-50 chance to decay in an hour, is the cat in superposition alive and dead until we open the box? That sounded crazy to some, but with amplitudes, it's amplitudes for decayed cat dead and not cat alive. When we open, we get entangled. Our seeing correlates with one or the other. But here's the thing. In real setups, like lab equipment from those days, big things interact with everything. Air molecules, light, heat. Those countless interactions act like measurements, making interfering amplitudes cancel fast. Superposition spreads, but coherence, the ability for arrows to interfere usefully, vanishes quickly. For anything macroscopic, a cat is breathing, moving, warm, trillions of particles interacting. No way for alive and dead amplitudes to stay coherent. We always see definite cat alive or dead. The rules apply the same, but the classical world emerges because interference washes out. That's how it works beautifully. We've built up from slits and reflections to this. Next time we'll dig deeper into why the cat isn't really in trouble, and how amplitudes resolve these puzzles without magic. We were talking about that old thought experiment from way back. A sealed box with a bit of radioactive material, a Geiger counter hooked to a hammer, a flask of poison, and a cat inside. The idea was that if the atom decays in a certain time, the counter clicks, the hammer smashes the flask, and the cat dies. If not, the cat lives. 50-50 chance, like flipping a coin. People got all worked up because if you follow the rules we use for tiny things, like electrons or photons, the whole setup, cat included, ends up with amplitudes for two possibilities. One where the atom decayed, and the cat is dead, and one where it didn't, and the cat is alive. Adding those arrows before squaring would mean the probability is a mix. So until someone opens the box and looks, is the cat in some crazy state of being both alive and dead? That bothered a lot of smart folks back in the day. It still does some, but let's see if we can make sense of it without any magic. First off, nobody really understands this stuff completely. It's wild, and it doesn't match our everyday experience. But the calculations work every time, better than anything else we've got. The key is to stick with the amplitudes and paths all the way. Every possible history of the system gets an arrow. For the atom alone, isolated, yes, arrows for decayed and not decayed add up nicely, and you can see interference if you set up the right experiment. We did things like that with atoms in the labs during the 60s, cooling them or trapping them to keep them from bumping into too much. But hook the atom to a Geiger counter, and that to a hammer, and that to poison gas filling the box, and then a cat breathing it. Now you're talking about a huge number of particles all tangled up together.
Each history branches into millions more because of interaction. The cat isn't just sitting there quietly. It's warm, breathing air molecules, fur vibrating a tiny bit from heat, eyes moving even if closed, heart pumping blood with trillions of atoms jiggling around. In one set of histories, the atom decays, poison releases, cat's lungs fill with gas, cells stop working, cat dies. In the other set, no decay, no poison, cat keeps breathing happily. To get interference between those two big bunches of histories, like alive cat arrows adding to dead cat arrows, you'd need the arrows from all those detailed paths to line up in direction phase after phase. But they don't. The environment, the air, the box walls, thermal radiation, everything is different in the two cases. In the dead cat histories, molecules are arranged one way. In alive, another. Those differences make the stopwatch hands spin at slightly different rates for different paths. It's like trying to add arrows that are scattered all over the place randomly. Most cancel out in pairs or groups. The net arrow for interference between alive and dead becomes tiny, practically zero, way faster than you can imagine. Take electrons going through slits. If you let air molecules bounce off them or even shine dim light to see them, the interference pattern washes out. The more interaction, the quicker it goes. Classical. 2 clumps instead of stripe. Scale that up to a cat with something like 1025 atoms, all interacting differently, depending on whether poison hit or not. The off-diagonal terms, the interference between alive and dead, vanish in a fraction of a second, way before anyone opens the box. So inside the box, even closed and dark, the amplitudes have already spread and cancelled any coherent mix. What's left are 2 separate bunches. One big arrow for cat alive, probability about 50%. One for dead, the other 50%. No overlap, no interference. When you open the box, you're just hooking yourself into one bunch or the other. Your own amplitudes branch. You're seeing a live cat, or you're seeing dead cat. But each version of you sees a definite cat. No special role for observation or consciousness. Any interaction that records the difference does the job. The cat itself knows because its parts are entangled differently. The air knows. The box knows. The same amplitude, adding that works for photons bouncing off glass, or electrons hitting screens, works here too. It just looks classical fast for big things because so many paths get involved. Think back to partial reflection. Why does light partly reflect off a window pane? Arrows from front surface and back surface. For thick glass, many little contributions from deeper layers, but mainly front and back. Depending on thickness and wavelength, arrows add or cancel. In everyday thick glass, like car windows in the 50s, the thickness varies, and light has many wavelengths, so averages to about 4%. But with careful thin layers, like those anti-reflection coatings starting to show up on camera lenses in the 60s and 70s, you could make arrows cancel almost perfectly, almost no reflection. For isolated tiny systems, arrows from different possibilities stay lined up. For big systems coupled to messy environments, arrows scatter, interference dies quick. Experiments bore this out. By the 70s and 80s, we were seeing superposition in bigger and bigger things. First atoms, then molecules, with dozens of atoms, even little vibrating mirrors in labs. But the bigger and warmer, the faster coherence fades. Record short times for large objects. Nature doesn't allow stable macroscopic superpositions to hang around. Rainbows come from light, taking many paths through drops, arrows adding beautifully. But try to see a rainbow from a single definite path. It doesn't work. Same here. We see definite cats because interfering paths cancel. So the puzzle isn't that the rules break for cats, it's that the rules give classical behavior automatically. When things get big and complicated enough, the amplitudes go all the way down and all the way up. No cutoff needed. That's the beauty of it. Same simple idea. Add arrows for every path. Square the final one for probability. Explains why tiny things interfere wildly and big things look ordinary. We calculate probabilities for radioactive decay, triggering counters in labs all the time, and it matches. Just happened to be on the ordinary side. Nobody said it would feel intuitive, but it works, and that's how nature does it. As far as we can tell, we've come a long way from bullets and waves to arrows and paths. Next, maybe we'll talk about how this picture leads to all the forces we know, or spin, or other fun puzzles. But for now, think about those little arrows spinning away, summing up the world.